Almost every chemical reaction requires heat to either be transferred into or out of it. And we describe that energy, that heat energy, as the enthalpy of the reaction. When we look at chemical equations, we've been looking at chemical equations as very simple chemical species equations, but we can also look at something called a thermochemical equation. So starting with a very simple reaction, this is actually just a physical change, liquid water going to gaseous water. We need to add heat in order for that to occur. So we could write that as heat plus liquid water gives us gaseous water. So now this is a little bit more of a thermochemical equation that incorporates heat, but we know how much heat it requires. There's a known heat of vaporization here, so we can include an actual number in there. If we look up heat of vaporization or enthalpy of vaporization, we find 540 calories per gram. When we're in a chemical equation, we usually don't work in grams directly. We work in moles, so we can convert grams to moles here, and we can get something that tells us that 9.73 kilocalories per mole of water plus liquid water gives us gaseous water. This is a thermochemical equation, right? And the way it's often written, the way it's usually written as is the chemical equation plus this delta H, this enthalpy of reaction, written separately. And because heat is required, that enthalpy is endothermic and has a positive sign. So how do we work with those thermochemical equations? Well, again, we've got that delta H of reaction, and what we really want to get to here is differentiating between endothermic and exothermic reactions. So if a reaction now requires more energy than it liberates, that reaction is called endothermic. So the net energy flow there is energy going in, heat energy, in the case of enthalpy, going in. And those are all of the energy going in or out is due to either breaking or forming chemical bonds and interactions. One way we can look at this is graphically by using something called a reaction coordinate diagram. So a reaction coordinate diagram, let's just start with an axis set. And how are we going to label those axes? Well, the vertical axis here is energy or heat. We're going to talk specifically about heat when we talk about enthalpy, but this can be used for general energy description as well. And then this x-axis is our reaction coordinate. And a reaction coordinate is really anything that we can monitor to watch the progress of a reaction. So on the left of our reaction coordinate, we're more on the reactant side, right? Just like in a chemical equation, on the left is reactants. And as we move left to right, we're moving from reactants to products. So my reactants are at the beginning of my reaction coordinate. As my reaction proceeds, I get to the product side of my reaction coordinate. And comparing these two levels, right? Comparing these two heat levels, we can now look at delta E or delta H of reaction and use this as a way to visually compare reactants to products. There are a couple examples in your book that look just a little bit different. They're the exact same thing. So let's take a look at them. Again, progress of reaction, that's reaction coordinate, and amount of energy. If we start up here, just like in the last example, if energy is given off, if this is an exothermic process to get from reactants to products, we've got what's often referred to as a downhill reaction. If we look at the other possibility, what if we have to add energy? What if it's an endothermic process? We go from reactants to products in an uphill process. It requires energy, so this would be endothermic. One of the nice things about reaction coordinate diagrams is we can use them to not just look at single step processes, we can use them to look at multiple step processes. So if I've got reactants and products, and let's say it goes through a couple steps, I turn my reactants into the first intermediate, and well, in this case, that required energy, that required some heat, so I had to add heat into it. Intermediate 1 goes to intermediate 2, that liberates energy or liberates heat, and actually liberates quite a bit according to this picture. But then going from intermediate 2 to products now requires heat again. So I can look at that stepwise process, or I can just look at the overall process, look at reactants and products, and my products are a little bit higher in heat, higher in energy than my reactants. This is overall an endothermic process. We're going to use reaction coordinate diagrams in a lot of things, so this was just a good way to introduce them and get started thinking about them. We'll have lots of opportunities to re-explore these. See you next time.